Right, so 4.5 is probably going to be the learning objective that takes the longest amount of time because you have to solve an entire related rate problem just for one multiple choice question. All right, this first one is actually the most difficult question on the whole page. All right, so a tube being stretched. We know how the height is increasing, so I'm going to highlight the importance of the height is increasing at some rate. The radius is exactly 6, and the volume is increasing at 96 per second. All right, so our final answer we want is something about the surface area. All right, and they give us the equations, or at least I gave you the equations. I think they also give you these equations as well. All right, but so volume is pi r squared h, surface area is just 2 pi rh. So the first thing I have to do is I'm going to take the derivative of both of these equations. So the left-hand equation is going to turn into dv over dt. All right, so I'm going to separate into pi r squared and h, all right, because it's r squared times h, so I have to do the product rule. So pi r squared stays, and dh dt is the derivative, and I add h stays, the derivative of pi r squared is going to be 2 pi r dr dt. I'm also going to do it for surface area. I'll just use capital S, so that way there's not 2 letters. And 2 pi r times h, so 2 pi r is going to stay. The derivative of h is dh dt, plus h stays. Derivative of 2 pi r is 2 pi dr dt. So our final answer we actually care about is for the surface area. So we want to plug as much stuff into this bottom equation as we can. All right, so what do we know? We know the radius at this exact moment we care about is 6. So this is going to be, where I'm going to have room to write this. Let's write it up here. So we have 2 pi, r is 6. The h dt, the height is increasing by 2 millimeters. That means the change in the height is 2. So that's going to be a 2. Plus h, I don't know what exactly the h is right now, so I can't plug anything for that. And I don't know what dr dt is because I don't know how the radius is changing. I just know the actual radius. All right, so that's all I can plug in for now. But let's go to the volume equation and figure out what I know. I know the volume is changing by 96 pi. I know at this time the radius is 6. The height is changing by 2. Again, I don't know h, but I do know r. R is 6. And I don't know dr dt. Right, so how is this going to end up helping me? Well, if you look here, there's an h and a dr dt here. There's also an h and a dr dt in this other equation. So if I can figure out what h times dr dt equals, I can plug it into the other equation. So how I'm going to do that, I'm going to subtract this to the other side. All right, so that's going to become, let's just write it down here. All right, so it's become 36 times 2 is 64, and then 96 minus 64 is 32. So that's going to be 32 pi on the left now. On the right, it's going to be 12 pi h dr dt. Oh, did I mess something up? Let's see. 6 times 6 times 2. Oh, that's 72, and then I do 96 minus 72. All right, so that's 24 instead of 32. So that's 24 there. Okay. And now I divide by 12 pi, so I get 2 equals dr h times dr dt. All right, so this thing, h dr dt, is equal to 2, so I can plug it into my second equation. The 2 pi is still going to be there, but that h and that dr dt is 2. All right. And now I put it all together. 6 times 2 times 2 is 24 pi. 2 times 2 is 4 pi, and I get 28 pi. All right, so I can eliminate C and D. And then 28 pi is a positive number, so the surface area is increasing. So this one, like I said, is the most difficult one because you have to relate these two different equations, and you're also doing this kind of weird connection of the h dr dt in both equations. All right, so that makes this one pretty difficult. I'll probably keep this one on the actual test, but just change the numbers. So I try to kind of figure out how you can relate these two equations. All right, something that, again, is kind of advanced, but it's something the AP test expects you to be able to do. All right, 14 is one that we've done before. We have this parabola, or hyperbola is xy equals 18. and we know some values, all right, what is true about x at this instance. So again, for all these ones, we're going to do the derivative first. We did a problem like this in the last learning objective. You have to do the product rule. And we did it in that last learning objective, so that's what we get. And we plug in what we know. We don't know x. We know dy dt is 8. We know y is 6. And we don't know dx dt. All right, well, there's two things we don't know, so we can't work yet. But what we do know is y is 6. We also know x times y equals 18. So that means even though it's not given to us, we actually do know that x is 3. So 3, 8, 6. All right, we subtract that to the other side. 3 times 8 is 24. And we divide to get -4. So the change in x is -4. All right, so we know the change is 4 units. All right, so the 1 is out. And again, since -4 is negative, it's decreasing by that amount. All right, it's decreasing by 4 units because we get a negative answer. All right, so we did this problem on one of our handouts. All right, but again, just take the derivative, plug in what you know. All right, this is another one that we did on one of our handouts. We had this cylinder that's leaking water. And we're going to figure out how, what rate is the height of the water changing at a specific time. All right, so the volume of the cylinder is given to us, the surface area of the cylinder is given to us. Again, if we're talking about water leaking, we're talking about the volume, not the surface area. So we actually don't care about the surface area at all, we just care about the volume, is pi r squared h. All right, another thing we saw when we were doing these related rates problems is if something is constant, you can plug it in at this point because it's not going to change throughout the whole problem. And the only thing that's not going to change with the water in this tube is the radius. It's always going to fill up that bottom circle, so the radius is always going to be the same. So I can plug in the radius of 1. All right, but the overall volume is going to be changing. The height is going to be changing as water is going in and out. So this is the equation we're stuck with. And now we take the derivatives. Again, remembering pi is a constant, so I'm just going to get pi to stay. And the derivative of h is dh dt. And then we plug in what we know. Water's leaking at a rate of 1 cubic foot per second. So the water moving out is going to change the volume. And the volume is going to be going down, so it's going to be -1. And we're trying to find how the height is changing. So we're trying to find dh dt. So I just divide by pi, and I get -1 over pi feet per second. I bet we did that exact problem on one of our handouts. And we've also done this exact problem on one of our handouts. And we had the spotlight shining on a wall with this guy walking. And he's going to cast this shadow on the wall. All right, he's going to be 5 feet high, and we want to figure out how high the shadow is. And I'm going to do it just a little bit differently than we did it on the handout. All right, so the handout solutions are on the assignment guide. So in the handout solutions, I put an x here. All right, but let's just say we could put our x in the other place. All right, so I could say this is the distance x that I am from the spotlight. And the other part of this triangle is going to be the whole distance, 40, minus that x part. But again, when you look at this picture, you'll see these two triangles. So we'll have this kind of blue triangle, which is the bigger one, and the red triangle, which is the smaller one. And the ratio of these sides are the same. So if I take h, the height of the blue triangle, over the base, which is the bottom, that's the whole bottom, which is the 40 feet from the spotlight to the wall. That's the same as the same sides of the red triangle, so the height is 5, and the base is x. And if I multiply both sides by 40, I get h equals 200 over x. And now I do my derivatives. H is going to turn into dh dt. 200 over x, all right, it's 200x to the -1. It becomes -200 x to the -2, all right, like that. And I took the derivative of x, so I get a dx dt. And here's where how you label your problem and what you plug in matters. So I'm trying to figure out how this height is changing. All right, what is x in this situation? Right now, my person is 10 feet from the wall, so this distance here is 10 feet, which means this whole distance is 30. So I'm going to put a 30 squared on the bottom. And how is x changing? The person is walking towards the wall, so he's walking this way, which means my x value is getting bigger, right? Because as he walks to the left, that x value is going to get bigger, so my value is positive 2. It's going to be negative 400 over 900, which is negative 4 over 9, and our rate is feet per second. All right, so it's the same answer we got doing it the other way when we had these two things switched. But just showing two ways. All right, depending on how you label your diagram, you can do the problem slightly differently. Just things are going to be a little bit different when you plug in different things. All right, we get that answer there. All right, 4.6, we didn't practice much in class, but there's only like one thing to know, and that's basically you can approximate a function using a tangent line. So for all these ones, you're going to create your tangent line and then plug in the value you want to approximate. All right, so here we're given that g of 4 equals 12, and we're given some specific values of g prime. So to make our tangent line, we do y minus y1 equals m times x minus x1. All right, our original values are going to come from our original function, so that's going to be the y value is going to be 12. Don't know the slope yet. X value is 4. All right, what's the slope of the tangent line? Well, that's our derivative exactly at 4, because we have to use the same point here, so that's going to be 2.2. All right, so that's our tangent line at the point 4. So you do that first. You don't worry about what you're approximating. Just do it at the point you know. And now I want to approximate at 4.2. So now I plug in the x value, 4.2, into my tangent line. All right, and you'll have access to a calculator for this. So you would do 4.2 minus 4, that's 0.2. 0.2 times 2.2, that's 0.44. Then I add 12. On the other side, I end up getting y equals 12.44. All right, so that's my approximation for the 4.2 using the tangent line at 4. And all these ones are going to follow a similar pattern. So for 18, I want to approximate f of 1, but I have all this information about f of 2. So I'm going to find the tangent line at 2 first, and then plug in 1. All right, so my tangent line, all right, my y value is 3. My slope comes from my derivative, that's negative 4. And my x value is 2. All right, so that's my tangent line at 2. And now I want to plug in 1 into this. And just simplify. 1 minus 2 is negative 1, so it's going to be positive 4. I'm going to get 7. Which is not an answer because I made a mistake. All right, so none of these answers are right. It's actually 7. All right, let f be a function, all right, where its slope is given by dy dx equals y squared minus x. And we know f passes through the point 1, 2. All right, so again, we're going to make our tangent line. All right, we're going to plug in our y value that we know is 2. Our slope we'll figure out in a second, and our x value is 1. And how do we figure out our slope? That comes from our derivative. So our slope is going to be y squared is 2 squared minus our x is 1. It's 4 minus 1, and that's 3. All right, so our slope is 3. All right, so that is the equation of the tangent line at the point 1, 2. And now I want to plug in 1.2. So y minus 2, 3 times 1.2 minus 1. And again, you'll have a calculator. So let's do 1.2 minus 1 is 0.2. 0.2 times that slope is 3. That's going to be 0.6. And I add the 2 to the other side, so I get 2.6 as my final y value. B. Right. And again, 20 is just the same thing without the answer choices. So if I want to approximate 1.1, the thing you have to know is you're going to approximate with the closest value you can. The closest value, x value I have is 1. So I'm going to use this middle row here. So I'm going to create my tangent line at 1 and then plug in 1.1. 0 and 2 are pretty far away from 1.1, so it's not going to give me a good approximation. So what I'm going to do is same thing we've just done a bunch of times. Our y value is 2 from our original function. Our slope is negative 3 from the derivative, and the x value we care about is 1. So that's the slope of my tangent line, and now I just plug in 1.1. right, and again, that's going to be 1.1 minus 1 is 0.1. Multiply that by negative 3 is negative 0.3. And then you're going to add 2 to the other side to get y equals 1.7. So that's our final answer, 1.7. Again, make sure you use the value closest that, to the thing you want to approximate. So that's why I had to use the middle row and not the top or bottom. All right, our last learning objective is using L'Hopital's rule. All right, so remember L'Hopital's rule, if you get 0 over 0 or infinity over infinity, you take derivatives and redo your limit. All right, this one we're trying to figure out the limit as x goes to infinity. All right, f of x is on the top. When I plug infinity there, I'm definitely going to get infinity. It tells me the limit of g is infinity, so I get infinity over infinity. So now I'm going to do, this is equal to L'Hopital's rule. I have to take the derivative of my f function. That's going to be 3 plus 6 e to the 3x. I remember when you do the derivative of e to the 3x, it's going to stay. You have to multiply by 3 because of the chain rule. On the bottom, I'm going to get the derivative of g that's given to us. It's just 4 plus 1 over x. And now I want to plug in infinity again. When I do that, e to the infinity is still infinite, so the top of this is still infinite. At the bottom, I get 4 plus 1 over infinity is going to go to 0. So on the bottom, I'm just going to get 4. All right, and infinity over infinity is bad, but infinity over 4, that I can actually do, and that just gives me a infinite value. All right, so on to the next one. Again, the first thing you always want to try to do is plug in 0. So we get sine of 0 is 0. The natural log of 2 e to the 0 minus 1, that's 2 minus 1, which is 1, which is also 0. All right, so that's just telling me I get 0, 0, so I had to do L'Hopital's rule. Big surprise, because it's in the section about L'Hopital's rule. So this is going to be equal to the L'Hopital's rule. Derivative of sine is cosine. The derivative of natural log is 1 over the inside. And then the chain rule says that multiply by the derivative of the inside, which is 2 e to the t. All right, when you have this fraction within a fraction, that's going to move up to the top. And in the bottom, it's going to have that 2 e to the t, which is not part of that fraction. And then I plug in 0 for all these. Cosine of 0 is 1. E to the 0 is 1, so it's going to be 2 minus 1 over 2, which is 1 half. All right, cosine of pi over 2 is 0. 2 times pi over 2 minus pi is 0. So again, big surprise, you have to do L'Hopital's rule. 3 cosine of x is going to turn into negative 3 sine of x. Denominator is just going to turn into 2. Again, remember the derivative of pi is just 0 because pi is a constant. And then I plug in pi over 2. Sine of pi over 2 is 1, so I get negative 3 halves. And last one, if I try to plug infinity here, I'm going to get infinity to the 0. This is one of the exponential ones. So what I'm going to do is do y equals x to the 1 over x. And now I take the natural log of both sides, because the natural log allows me to say that I can bring this exponent out, which is the natural log of x over x. And if I plug in infinity into that, I get infinity over infinity, so I can use L'Hopital's rule. So it's equal to, based on L'Hopital's rule, the limit as x goes to infinity of 1 over x over 1. And if I plug in infinity to that, which is just 1 over x, I get 0. 1 over infinity is 0. But the final answer is not 0 because that's equal to the natural log of y. So now I have to do e to both of those. So my final answer is e to the 0, which is 1. That's my final answer is 1. Right. So knowing this is the L'Hopital's rule section saves you one step because you're going to have to use L'Hopital's rule in every problem. But just do it correctly, taking your derivatives at the top, derivatives at the bottom, and then re-plug in your value. So that's our entire Unit 5 practice test. L'Hopital's rule is really important, but based on the calc thing, it's only one learning objectives. Related rates are pretty complicated, so those get broken up into 2 learning objectives. And we just have some other small things in there as well.